Imaginary numbers. If you recall, subtraction was invented to undo addition. The new operation of subtraction forced us to ask new questions. The number system before subtraction did not include negative numbers, and as a result of the new operation, a number system with negatives was created to give meaning to subtraction. The new question, what is the result of subtracting 7 from 4, required a new picture to tell the story. It was subtraction that led to the invention of negative numbers. They were called negative from the Latin word negare, which means to deny, since people denied that such numbers could exist. They weren't used much until the Renaissance and were only fully accepted in the 1800s. The inverse operation of raising a number to a power is to take the root of that number. The new system of numbers includes the negative numbers, which leads to a new question. What is the square root of a negative number? We don't have a simple answer to that question because no real number squared yields a negative number, unless of course we extend our number system to include numbers that answer the question. Just a quick reminder, the square root theorem allows us to find solutions to a quadratic equation. Here it is again. If x squared is equal to m, then we can square root both sides of the equation, and when we square root both sides, that's when we take plus or minus. So x is equal to plus or minus the square root of m, provided that m is greater than or equal to 0. It's worth noting that the square root theorem requires that we take the square root of non-negative numbers, and this restriction is the result of a number system that was limiting. It's also important to note or remind ourselves that if we were just told to square root a number, like to evaluate the square root of 16, the answer to this question, or when we evaluate this, it would only be positive 4. It is not the same as when we are told that x squared is equal to 16 and we have to square root both sides. When you have to square root both sides of an equation, that's when you consider the plus or minus 4. When you are simply evaluating square roots, you have to look at the sign that's in front of the square root and use the given sign when evaluating. Now that we've reviewed the square root theorem, let's discuss the new type of number that we have here, an imaginary number. Let there be a new number I called the imaginary number that has the following two properties. I squared is equal to negative 1, and I is equal to the square root of negative 1. By the square root theorem, if x squared is equal to negative 1, then we would have to square root both sides. And when we square root both sides, that's when we include the plus or minus sign in front of the square root. And the end result is x is equal to plus or minus I. There are two solutions, as there were before. I squared is equal to negative 1 by the definition above. And negative I squared is equal to negative I times negative I, which you can then rewrite as negative 1 times I, negative 1 times I, and then negative 1 times negative 1 is positive 1. These two negatives cancel one another out, and we are left with I times I, which is I squared, which is again negative 1. The primary solution when you are solving this x squared is equal to negative 1, the primary solution is the positive I, and the secondary solution is negative I. Let a real number be represented by an arrow attached to the origin. Positive numbers point to the right and negative numbers point to the left. The length of the arrow is a scalar, or the number's absolute value, or the distance that it covers. We learned earlier that multiplying an integer by a negative 1 doesn't change the absolute value, but instead reverses its sign or its direction. So if we multiply 7 times negative 1, we take the arrow and we flip it. The new number is the same distance from 0, but in the opposite direction. With the advent of imaginary numbers, there was a desire to create a visual metaphor to explain it, and mathematicians came up with a new way of imagining what it means to multiply by I squared, or -1. Rather than multiplying by -1, as explained as an arrow in the opposite direction, the new metaphor involved rotating the arrow 180 degrees counterclockwise about the origin. The results are the same, but the way one imagines arriving at the result is slightly different. Instead of it appearing as more of a reflection across 0, it can now be seen as a 180-degree rotation about the point 0. So if multiplying by I squared is explained as a counterclockwise rotation of 180 degrees, what might a counterclockwise rotation of 90 degrees mean? Well, that's where the regular I comes in. By letting multiplication by I mean rotating the arrow 90 degrees counterclockwise about the origin, a new dimension is introduced. So if multiplying by I is explained as a counterclockwise rotation of 90 degrees, what might a clockwise rotation of 90 degrees mean? It actually means multiplying by -I. So if we have 7 and we multiply it by -I, we can move clockwise, which is the opposite direction of counterclockwise. So that's where the negative comes in. And because it's 90 degrees, we bring the imaginary part in. So by letting multiplication by -I mean rotating 90 degrees clockwise about the origin, we get the results shown in the diagram. Therefore, we can let multiplication by I be a counterclockwise rotation of a number 90 degrees, and we can let multiplication by -I be clockwise rotation of a number 90 degrees. And multiplying I by I again, we rotate counterclockwise twice for a total of 180 degrees. And that explanation explains why I squared is equal to -1. And multiplying -I by -I again will rotate our arrow clockwise twice, 90 degrees, and then 180 degrees, which brings us back to -7. So this satisfies that -I quantity squared is equal to -1. We can now graph our real and imaginary numbers in what's called the complex plane. The horizontal axis is called the real axis, and it includes all real numbers, positive to the right and negative to the left. The numbers on the vertical axis are called imaginary numbers. When they are positive, they go upward, and when they are negative, they go downward. All the numbers have a direction and have a scalar, and 4 examples are provided in the in the complex plane below. We have 6 traveling positive along the real axis. We have -8 traveling in the negative direction on the real axis. We have 4i traveling upward on the imaginary axis, and we have -3i traveling downward on the imaginary axis. Just as people couldn't originally think of how 0 or negative numbers could be used, they also couldn't see how imaginary numbers would be of value. Mathematicians argued for centuries about imaginary numbers before coming to agreement about their existence and uses. Imaginary numbers proved to be very useful in real-world applications. It turns out that many physical systems, including alternate current electrical systems, rely on an understanding of imaginary numbers. If you think about it, if I didn't have any useful applications, it likely would have never been discovered. Let's see if we can find any patterns with imaginary numbers. Repeatedly multiplying by -1 does produce a pattern: 1, -1, 1, -1, 1, and so on. Now let's consider what happens when we multiply by I repeatedly. If we just have I, or I to the first power, we just have I. I squared, we know by the theorem, is equal to -1. I cubed, we have I times I squared. Well, we know I squared is -1, so we would have a -I. Now let's look at I to the fourth. That can be broken down to be I squared times I squared, which is -1, times -1, which is +1. Then if we have I to the fifth, we have I times I squared times I squared. So that'll be I times -1 times -1. That's +1 times I is just I. If we do I to the sixth, we would have I squared times I to the fourth. I squared we know is -1. I to the fourth we found out is equal to +1. So that's going to be -1 again. If we do I to the seventh, we will have I times I squared times I to the fourth. So that's going to be I times -1 times +1, which is equal to -I. If we do I to the eighth, we'll have I to the fourth times I to the fourth, which ends up equaling 1 times 1, which is just 1. Does anybody see a pattern in the solutions that were found? We have I, -1, -I, +1. I, -1, -I, +1. What generalizations can be made about I being evaluated to any exponent? And we also have a visual showing that I to the first is I squared is -1, I cubed is -I, and I to the fourth is +1. Take a moment to pause this video and think about the questions, and when you're done, unpause. The number I raised to the nth power for an integer n can be simplified into I, -1, -I, or +1 that we found as that pattern on the previous slide. If the power of n of I to the nth power is even, and the exponent is a multiple of 4, it will simplify to 1. And remember, we found that out when we had I to the fourth. It ended up equaling 1. The next time it happened was at I to the 8th power. That was also 1. Notice 4 and 8 are multiples of 4. The exponent, if the exponent is only a multiple of 2 but not 4, then it simplifies to -1. So when we had I to the 2nd power, that's -1. When we had I to the 6th power, that was also -1. If you go up a little bit further and do I to the 10th, that will also equal -1, because it's an even exponent, but the exponent is not a multiple of 4. If the power of n in I to the nth is odd, then you can factor out an I to create a product of I and an even power. So when we had I to the third, we rewrote it as I times I squared, because we knew that I squared was -1. And then you would use the properties of those I raised to different exponents powers to evaluate, and this became -I. So once you factor out an I to give you another I raised to an even exponent, you can then backtrack to the even exponents in order to figure out whether the result is +I or -I. Some of you may also have noticed that I to the 1st power is I, so was I to the 5th power. The next one that would be I to the 9th power. Notice each of these exponents, the 1, 5, and 9, if you were to divide each of these by 4, the remainder would be 1. So if you divide the exponent by 4 and it doesn't go evenly and the remainder is 1, then it will simplify to I. Let's also go over what happens with I to the third. I to the third gave us -I. So did I to the 7th. That gave us negative I. The next one that would give us negative I would be I to the 11th power. Notice, if we look at the exponents 3, 7, and 11, if we divide each of these exponents by 4, the remainder will be 3. If the remainder is 3, when you divide the exponents by 4, the answer or solution will be negative I. So that's another way to look at the odd exponents. Now let's try some examples. We're going to simplify each of these I being raised to various exponents. So the first one we have is I raised to the 87th power. We can rewrite that as I to the 86th power times I to the first power. Now 86 is an even number, so we can then rewrite it as I squared, because that's going to give us negative 1, and that would be raised to then the 43rd power, and we still have times I at the end. And again, I squared is negative 1, and we're going to raise negative 1 to the 43rd power, and then multiply it by I. Negative 1 to the 43rd power is going to be negative 1, and negative 1 times I will be negative I. The other way of doing this, if you're doing the remainder, like division by 4, if you do 87, it doesn't get divided by 4 evenly. It would be I to the 4th power raised to the 21st power times I cubed. So this I to the 4th is positive 1 raised to the 21st power times I cubed. That's going to be 1 times negative I, which is still negative I. So you can get the answer using either method. Now let's look at the next problem. We have I raised to the 64th power. You have the option to either write it in terms of I squared and get negative 1 raised to a power, or you could put it in terms of I to the 4th power. I'm going to write it as I to the 4th power because that's 1, and I to the 4th power raised to the 16th power will give us I to the 64th power. So therefore, I to the 4th power is positive 1, and we're raising it to the 16th power, and 1 raised to the 16th power is just going to be 1. Now let's look at the next problem. This one is a little more challenging. I'm first going to rewrite it as negative 1, because that's what this negative value is in front here, times I to the 18th power, and we can rewrite I to the 18th power as I to the 2nd power raised to the 9th power. So we have a negative 1 from the beginning, and then I squared is also negative 1, and it's being raised to the 9th power. Well, negative 1 to the 9th power is going to be negative 1, and then we have this other negative 1 that's out in front, and negative 1 times negative 1 is positive 1. Now let's look at our last problem. Again, we are going to first rewrite it as negative 1 times I raised to the 27th power. Now, I raised to the 27th power can be rewritten as I to the 4th raised to the 6th power times I to the 3rd power. 6 times 4 is 24, and then we have 3 remaining. So we have a negative 1, then we have positive 1 raised to the 6th power, and I cubed we have found is equal to negative I. So this 1 raised to the 6th power is 1, and then we have negative 1 times a negative I, so we're going to have positive I as our final answer for this problem. And here are the solutions to each of these problems. They do match the solutions that we found. Sometimes instead of doing I to the 4th, they did I squared. So this was negative, and then negative 1 to the 9th. So a negative of negative 1 is still positive 1. And here, instead of doing I to the 4th raised to the 6th power with an I cubed left over, they just pulled out one I and then did I squared to the 13th. So I squared to the 13th is negative 1 to the 13th, which is negative 1, and then negative 1 times negative 1 is positive 1, and we still had this extra I left over. So there are some alternative ways or different ways that these examples can be simplified. Now let's have some more practice problems dealing with I raised to various exponents. The first one we have is I squared plus I to the 4th. Well, I squared is equal to negative 1, and we are adding I to the 4th. That is equal to positive 1. Negative 1 plus 1 is equal to 0. So that's our final answer for the first one. In our next problem, we have 5 times I raised to the 104th power. Well, 104 is not only an even number, but it is also divisible by 4. So that means we have 5I times I to the 4th raised to the 26th power. I to the 4th is equal to 1, so we have 5 times I times 1 raised to the 26th power, and 1 raised to the 26th power is 1. So we just have 5I as our final answer. Now let's look at our third one. We have 8 times I raised to the 102nd power. So we have 8 times I squared times I raised to the 100th power. Well, 100 is divisible by 4. So we have 8 I squared times I to the 4th, which is 1, raised to the 25th power. So we have 8 times I squared. I to the 4th is 1, raised to the 25th power. It's still 1. So we have 8 times negative 1. And 8 times negative 1 is going to give us negative 8. Now let's look at the next problem. We have a negative 1 that's out in front, and then we have I to the 89th power. That's I times I to the 88th power. I started writing my exponent before I wrote the I in there. And I to the 88th power can be rewritten as I to the 4th raised to the 22nd power. We have a negative 1, and we have an I. Well, I to the 4th is 1. 1 raised to the 22nd power is 1. So we just have a negative 1 times I, which is negative I, as our final answer for this problem. And now we have one more remaining. We have I raised to the 4 millionth power. So that can be rewritten as I to the 4th raised to the millionth exponent. And I to the 4th is 1, so the 1 millionth exponent is just 1 as our final answer. And here are the solutions to each of these practice problems, and they do match the solutions that we found.